Good morning, ladies and gentlemen. So we're going to discuss in this video Calc Review 7 and 8, both of those worksheets. One of them was rectilinear motion, the third installment of rectilinear motion, and this one was rectilinear motion when you're given a table of value problem. And then we'll go on to Calc Review 8, in which we are given a graph of f prime, and we have to sort of answer questions about f or f double prime or even f prime. So when you're given a table of values like you are in this problem that you're looking at here, typically you're going to be asked a lot of questions about approximations, right? Because if we don't have the function defined as an expression, and all we're given are sort of a set of points that exist on that function or its derivative, then we are stuck using approximation methods. So you can expect that you'll need to use a Riemann sum, or that you'll need to find the slope of a secant line to approximate the slope of a tangent line. So things like this. And in fact, that's what occurs, I think, in part A. You're finding the slope of a secant line on the velocity function in order to approximate the acceleration at a particular point in time. Part B, approximate this integral using a Riemann sum. Part C is just asking about the intermediate value theorem. Okay, so that's not an approximation, but it does make, it uses the information given plus the information given in the table, plus the fact that, the situation being modeled here is a person riding a unit cycle back and forth, and you're told that the function is twice differentiable. So that, of course, is going to lend itself to either the mean value theorem or the intermediate value theorem. And so that appears in part C. And I'm happy to go over those problems if you request them in the future. But for this video, I'm going to go over part D, which was a problem that I discussed in an SGI with a student. And I think it's definitely worthy of discussion. So part D says that a light is, well, actually, let's set up the problem once again. So again, the situation is there's just this sort of linear track that starts in the west and heads east. So it's a west to east track. And the function up here, b of t, that we're given is the distance between Ben, let's say Ben is at point B, the distance between Ben and the westernmost edge or end of the track. All right, so that's this function b, and v is Ben's velocity at any particular time. So you could actually, of course, think of v as b prime of t. All right, so they're the same thing. All right, so that's the situation. And Ben, just as time goes on, Ben is kind of changing his position along this track. Okay, great. Part D now adds to the situation. They say a light is directly above the western end of the track. So if you can use your imagination, this is some light source, and it's drawn directly above the western end of the track. Ben rides so that at time t, the distance between Ben and the light. Now, that distance is this dotted line that I'm drawing now. This is the distance that they are referring to with this new function L of t. And hopefully you can see that as Ben changes his position along this track, L of t also changes. And they are also telling us that this distance, L of t, satisfies the equation L of t squared is equal to 12 squared plus b of t squared. Hopefully you recognize that equation as the Pythagorean theorem. If you're drawing the diagram, it should jump out at you as well. So notice L of t is the hypotenuse, so that makes sense. B of t, of course, is this distance between the westernmost edge and wherever Ben is at any particular time, which kind of implies, they don't explicitly come out and say it, but that implies that the light pole here is 12 units tall. Do they give us units? Yeah, meters. So this light pole or light post is 12 meters tall. All right, so we have the diagram, and whenever you're given a situation like this, I strongly, highly recommend drawing a diagram. But again, that's completely up to you. But now that I have the diagram in front of me, I clearly understand that we're dealing with a right triangle here. And the question goes on to say, at what rate, that's a very key word, is the distance between Ben and the light changing at time t equals 40? So we're talking about a rate of distance between Ben and light. So we're talking about a rate of L of t, which of course is, this whole sentence is asking us, at this particular time, it's asking us to find L prime of 40. Right, so that red underlined sentence can be boiled down to L prime of 40 equals what? All right, so let's go ahead and see if we can figure that out. The good thing is we have an equation, and while that equation might not have L prime, it does have L. And of course, in order to obtain an L prime, we just need to differentiate. In this case, we're going to differentiate with respect to time. All right, so let's write down that equation. We have L of t squared is equal to 12 squared plus B of t squared. Now, let's look at each of these terms. L of t, this distance between Ben and the light, that is a function of time. As time goes on, Ben is moving, and thus L of t is changing. B of t, of course, is also a function of time. As time goes on, Ben is moving along this track, and thus his distance, the distance between point W and point B, will change. The light post, however, is not a function of time. The light post is 12 meters tall and will stay as 12 meters tall. So that's something to keep in mind when we differentiate with respect to time. Remember, a derivative is how is this function changing at that instant of time? All right, so since L of t is a function of time, when I differentiate with respect to time, I have to use that power rule. But since this is a composition, right, this is a function within a function, I need to use the chain rule. So the derivative, this is implicit differentiation, which tells us we need to use the chain rule. Okay, so we have 2 times L of t times L prime of t is equal to, all right, now what's the derivative of 12 squared with respect to time? Well, that's just 0. And that basically should make sense, because that just tells us that as time moves on, the light pole is not changing height. And now we move on to this last term, same as what we just saw with the L function, power rule, chain rule. Okay, we have this equation. Now it's just kind of a matter of filling in what we know and solving for what we don't know. So let's take a look up here. What do we know? Well, we happen to have some information when t equals 40 in this table. We're told what B of t is, and we are also told what B prime of t is. So let's fill in that information. I forgot to look. So B of t is 9, B prime of t, or B of 40, I should say, is 9, and B prime of 40 is 2.5. The left side, we have to do a little bit more work. We don't have L of 40, right? We don't even have any information on L except for the fact that L is related to B in this way. And so we could actually solve for L of 40. I'm gonna kind of do it over here. So L of 40 squared is equal to 12 squared plus B of 40 squared. Okay, so L of 40 squared is equal to 144 plus, what did we say B of 40 was? I think 9. All right, 9 squared, which is 81. And let me just pause for one moment. All right, and of course this gives us 225, and so the distance between Ben and the light post when t equals 40 is 15 meters. And we're going to use that information in this equation down here. So we have 2 times 15 times L prime of t. I still don't know that, but hey, that's what I'm solving for in this problem. And that's the only unknown in this equation, and therefore algebra will solve the problem. So L prime of t is equal to, the 2's are going to cancel. I have 9 times 2.5, use parentheses actually, all over 15, and whatever that happens to be. Those units, of course. So let's think about this. L of t represents a linear distance. So L of t will be measured in meters. Well, that means L prime of t will be meters per time unit, and time units are seconds here. Okay, it's really a good idea anytime you're given units in a problem, your final answer should include units. And there you have it. At what rate is the distance between Ben and the light changing at t equals 40? Oops. Actually, when I start plugging in values, we are actually evaluating this equation at 40. So it is proper to plug in that time period or that time instant into the function that we're solving for as well. But the rate of change in the distance between Ben and the light at t equals 40 is equal to whatever this number breaks down to be. Okay, there you have it. Yes, is that involved? It was. It's a part D of an AP problem, and so you can sort of expect something like that on your AP, I'm telling you. All right, so just be prepared, take it step by step, draw a diagram, and just kind of understand what it means when they say the word rate. If you see the word rate, the first thing that should jump into your mind is derivative. Okay, let's move on. This was the next day's assignment. So we'll do a few more lessons on this. And this is just analyzing graphs. Notice here, this is really important. Anytime you're given a graph, really pay attention to what type of a graph you're given. We are given the graph of f prime. Okay, so if they say, what is f of 3? The answer is not 4. This coordinate is f prime of 3, which is 4. All right, so we have to really pay attention to that. I was requested to go over problem part B on this, and so that's the only one I'll talk about. But again, if it should come up that you attempt this problem maybe a little bit later and you say, oh, part C gave me a lot of trouble, let me know. I'm happy to go over it. All right, so let's talk about part B. We want to determine the absolute minimum of f. So we want to find the absolute minimum of a function that we're not given. We're given f prime. And they use the phrase closed interval. All right, so a few things here. absolute minimum, closed interval. This should indicate to you that when we go ahead and find this minimum for this problem, we're going to be using the table of values. So, yeah, this is x. We're going to take an x value. We're going to find all the candidates for minimums. And once we do find them, we're going to plug them into the function f. And we're gonna evaluate f at these candidates. Whichever one happens to be the minimum in this table of candidates is the absolute minimum. You might be wondering, well, how can we evaluate f at those values of x if we don't know the equation for f? Well, we're going to talk about that. First, let's establish the candidates. So the candidates are always for something like this, the candidates are always the endpoints on your interval and the critical points. And remember, the critical points, I mean, we all remember, oh, that's when f prime is equal to 0. Yes, but also we have to check out for when is f prime undefined, because those also count as critical points, and those are also potential max or min values for a function. All right, so the endpoints are very easy. Our interval starts at 0 and ends at 8. So there we go. Now let's go on to find out the critical points. So when is f prime 0? Well, the good thing is I'm looking at a graph of f prime right now. And so it's very easy for me to pick up on when f prime is equal to 0. So it looks like f prime crosses the x-axis here, here, and here. And that is when x is 1, 4, and 6. So these are 3 new candidates, 1, 4, and 6. All right, so we do have a lot of candidates to deal with, but that's okay. It's actually going to be kind of simple once we get everything set. And now the last thing though, so we found when is f prime equal to 0. What we haven't yet done is looked into when is f prime undefined. Well, as you can see, just looking at the graph itself, you could see that f prime is a smooth continuous curve, and therefore f prime is defined at every single one of these points on this interval. And so there are going to be no points where f prime is undefined. All right, so now those are the only possible answers. Let's go in and figure out which one is the correct answer. So they kind of gave us an initial condition, but they're being tricky here. They're telling us that the function, the value of the function, the original function, not the derivative, the value of the original function when x equals 8 is 4. So we actually do get one of these values for free. Now the rest of them, we have to use that initial condition plus the idea of integration in order to get the values for f of 0, 1, 4, and 6. So we're going to do some of this work over here. So the equation, actually let's talk more generalities. The equation f of b, so the value of a function at point b is equal to f of a plus the integral from a to b of f prime of x dx. So if I want to find the value of a function at a certain point, what I need is some anchor point, some initial point, and then I integrate the derivative from that initial point to the point of interest. Okay, remember what this gives us is the net change in f. Okay, battery mode. The net change in f from x equals a to x equals b. All right, and I mean, another way to justify this is, how do I know that that's the net change in f? Well, think about what the fundamental theorem of calculus says. When I have a definite integral, I take the antiderivative and evaluate it at the upper bound minus the antiderivative evaluated at the lower bound. And so this integral is literally f of b minus f of a, which of course is the net change in f from x equals a to x equals b. All right, anyway, that's a brief reminder of how we would go about solving something like this. And let's actually do it now. That's the hard part. So we want 3 of these. F of 6. So let's just set up the equation. Well, what's our anchor point? What do we know? We know f of 8, so we're going to have to start there. Oops. And what do we want to add to it? Well, we want to add to it the net change in the function from starting at 8 and heading to 6. So that's why things are a little tricky here, because in this situation, we're actually starting at a higher x value and we're traveling to a lower x value. All right, so a graphical representation of an integral, of course, is an area under whatever function you're integrating. So if we're integrating f prime of x dx, that's just really saying find the from 8 to 6, it's saying find the area under the curve of f prime from x equals 8 to x equals 6. So let's go ahead and do that. The important thing to understand here is we're traveling to the left. So here's where x equals 8. Here's where x equals 6. We're traveling to the left. So even though the area is above the x-axis, which means our rectangles have positive height, they actually have a negative width because dx is decreasing from 8 to 6. Well, x is decreasing from 8 to 6, and therefore dx is negative. So we would actually, in this particular situation, take that area to be -7. All right, so this is f of 8, which is 4, plus -7, which of course is -3. Okay, so that's f of 6. Let's do f of 4. Now, the interesting thing is we now have like new information. We have f of 6, so we can go ahead and start from there if we want. And to get f of 4, we take that starting point of f of 6 and we integrate from 6 to 4 f prime of x dx. So that starting point, f of 6 is -3 plus, now I have to determine the area. Okay, so here's where x equals 6 to x equals 4. Again, we're traveling from right to left, so my dx's are negative, and in this case, my heights are negative. So the area of a rectangle would actually end up being positive because negative times negative is positive. So this actually ends up giving me a +3. All right, so this tells us that f of 4 is equal to 0. And I'll go through the others a little bit more quickly. So f of 1, I'm gonna again start at my new information, which was f of 4, and I'm gonna integrate from 4 to 1. F of 4 was 0. The area under the curve from 4 to 1, the area itself is 6, but since we're integrating from right to left, that means these rectangles have a negative width with a positive height. Ultimately, that's a negative area for our purposes. So f of 1 is -6. And finally, f of 0. I'm going to start from f of 1. Okay, so I have -6 plus the area from 1 to 0. Again, we're moving right to left. We have negative width, positive height, which is ultimately a negative area. So this is an area of -2, which gives us -8 overall for f of 0. And now our table of values clearly tells us that the absolute minimum is -8. So our final answer would, and by the way, the whole justifying your answer, all of this work that we're doing down here, this is the justification. So I'm not saying you necessarily have to show all of this detail, but I think setting up each one of these expressions, these integral expressions for each one of these problems is going to be key. But anyway, this is your justification. And then all we finally have to say is that the negative value, the minimum the absolute minimum of f is -8. This occurs when x equals 0. And there we have it. Again, so that was only part B. So this one, there's a lot of work involved, especially for part B, but I do fully expect something like this where you're justifying an absolute min or maybe a local min. If it's a local min, you just need to use the first derivative test, determine does the derivative change from positive to negative or negative to positive. And that's how you determine if it's a max or min. All right. So that's it. I hope you are enjoying, somewhat more relaxed week for your spring break. Next week, ladies and gentlemen, we're going to sort of really hit the ground running and do some daily exercises because that AP exam is right around the corner. So if there are any more questions on either one of these problems or any of the problems I've assigned this week, please let me know. But until then, ladies and gentlemen, have a nice weekend and hope all is well. Bye.